Yeah, my name is Marcelo, and I'm going to present a work that I did with Paul and Arthur in Geography. And it was published in the Uncertainty in Artificial Intelligence 2 years ago. I assume that you are familiar with Bayesian modeling. So what we want to do in the prior predictive distribution is that we wanted to define prior distributions without carry on with Bayesian inference, but we don't want to talk about the parameters. We want to ask questions about what is observed, the data that you are working with, because usually this is the case where you have data and then you need to choose a prior, and sometimes the prior is not really easy to understand because it relates to a parameter that's not interpretable. And of course, when the prior it's well defined and it represents the expert belief quite reliably. So what we will do basically, we will acquire information from the expert, asking questions about observable data, how it should look like, and remember that we have, what I'm saying is that we have qualitative information, and you want to transform that into a quantitative information and in the form of a prior or probability distribution. And in this way that I'm approaching, I also present some measure of model fitness to expert data. So let's recall, like, basically what we do in Bayesian modeling. We first have distribution for your data, like some of you call likelihood, but at this point I would like to call it just the data probability distribution, condition on the parameter, and given the parameter, how the data or the uncertainty of the data would look like, and then I define a prior for theta. Now, and usually in practice, what happens is that conditioning on this red star on theta, I have a sample. Usually it's IID, that's seen in that way. And once I have that sample, I use Bayes theorem, and then it gives me posterior, and I summarize all the information with respect to theta. Now, the prior distribution usually has parameters. You can call hyperparameters, just another level. And if you're, let's say, truly Bayesian, I don't want to say truly Bayesian, but if you're doing Bayesian, usually it's nice that the data, that the parameter comes before seeing the data. So you shouldn't look to the parameter and the data and figure out what the data would look like given a value of the parameter. Now, so given these two probability distributions, the y given theta and the distribution for theta, I have a Markov distribution if I integrate it over theta, which now depends on the hyperparameters lambda. So so I have marginalized the effect of the parameters, right? I don't have the effects of the parameters anymore. This should be the interpretation of this probability distribution. So, and then what is the prior predictive? What are we really going to do, like in a more general way? Given the prior predictive and the likelihood, or the data probabilistic model, find what would be the value, the distribution of theta that the previous equation would hold true. So given like on the left side and the likelihood, what would be the function of theta that this equality would hold? That's the idea. And again, let's not make the confusion with the data probability distribution and the likelihood, because the likelihood is formed once the data is given. And at this point where I'm talking, I don't have any data yet. Okay, so in practice, that no one will provide a functional form of the prior predictive, because in a case that the data is continuous, the density, I will talk. It wouldn't be easy to talk about the density, but I could. Where we're talking about, talk about what the data would look like. That's easy for an expert if he's well known with his own data. I mean, he works with some application, maybe in biology, and he knows how the population increases over time. He has experience from that. He has observed the data, and there's a probabilistic model for that. And the idea also comes from like late 80s, where Cadian has a very interesting paper that he uses similar ideas here. Actually, kind of took that idea from his papers. He mentions that it's the closed distribution that would represent opinions purely on the data. But that, well, you can argue about that. Yeah. So what will you do? Just think that this omega is the set of all outcomes of your data, right? What you're looking at. You have your Excel spreadsheet and so on. Now think that there are some sets of that data set that for you it's more problem than others. The second bullet point just tell you that. And you can, for different people might have different opinions about how the data would look like. But then for certain subsets of the data, you give some probabilities, right? And you just give some probabilities for certain subsets of the data that the sum of the probabilities that you have given, it sums to just to satisfy the usual rules of probability. Yeah, so just for example, you usually have, can I? Yes.
Oh, not there. Sorry.
Right. So if you imagine a Gaussian and you have some data points here, right? There's some intervals you can think that are more problem than others. For example, this interval here, I call, let's say, AI or AJ. You might think that this has certain probability and this has certain probabilities just by your experience in looking at it. So this is going to be our data, the probability of certain subsets, right? Now the interesting part of it is that the way that I'm asking the questions about the data or your experience in answer this question about how the data would look like, it's different from person to person. And so there is uncertainty because your experience is different, or because the way that I have asked you the questions, or many sources of different ways of proceeding the elicitation structure would influence you the way that you give the answer. So there is a paper in 90 from Ferguson that says that actually gives you a way of modeling probability distributions, which is called the issue process. Basically, what it's saying is that I have a probability model over probability distributions, and saying that I can model different probability distributions. You could tell me, I could have different persons answer different questions about how the data set would look like, and I could draw many probability distributions from this initial process to represent this procedure. But then I have to assume that this base measure is now our prior predictive distribution with a certain parameter alpha, and that parameter alpha has an interesting interpretation, as we'll see. Now, this digital process still depend on the parameters of the prior, the hyperparameters, and this is what we are interested in. To know, once we know these hyperparameters, we know the prior. So basically, then I can construct a likelihood function because P now is given. I have a vector of probabilities. We're going to make clear with an example, and then I can make inference on alpha and lambda. So as I said, the digital process captures the uncertain specification of the predicted probability, and then the role of alpha is to check whether the predicted model matches well the expert's opinions about the probability data. And you can show that actually it's just the inverse of the KL divergence, which is pretty interesting. So how general it is? Quite general because it can work from multivariate distributions. And of course, if I have two outcomes in my data set, simultaneous outcomes, this is going to be harder because I have to divide the space. It's harder to divide the space, but most of the applications what they have, have a line, and then the covariates, and that covariates are associated parameters, and those lines like one-dimensional observation, so it's easy to ask about one-dimensional outcomes and with many parameters. So as I said, covariates can be easily included, and so we can also recover multivariate power distributions, even though this might be a little bit more complex. And this can be used in hierarchical models as well. So let's go for an example. Maybe these things are more clear. So imagine that I have basic information about how we grow, like over time, how a human being grow for male and female. I have this set of information that at T0, the stature of a baby born is around 4.5 centimeters, and some other informations during the period of 2.5 years old to the youngster, almost constant growth stature, and so on. And after 17 years old, that would be like the high of for a male, and similarly for a female. Then what we did is we took the deterministic model for human growth in this paper, 1978. So someone wrote it, and it has 5 parameters: H1, T star is 0 and S1. These first 3 ones, they do have a nice interpretation, but S0 and S1, they don't have any interpretation. They are just constants that model the shape of the curve, the form of the curve of the human growth. So it would be hard to ask about them. But if I'm not wrong, the H1 is the average height. The T star is the time when there is this growth spurt in young age, and the HT star is the average height at that time. So what we did, just an example so for each time T, YT represents the stature or the height, given theta or these 5 parameters. And then we put in the expectation of y that would follow these deterministic human growth models. So, but then in the end we give a prior. We don't know what is the prior, or we don't know who is AD or BD. So in the end we have 10 parameters set, and it would be harder at this for me already to tell about these parameters, what they would look like, but with the information that we give previously, we could just talk about what the data would look like at certain time points. And this is what I did. So let's put like this. We fixed it like 4 periods of times, and at each time t, we asked about what the probability of the data, how the data would look like, and we first used the cumulative distribution. But this is just a probability, and then we made the difference of these probabilities. Then we have, let's say, a probability vector, and how maybe this figure will explain a lot more. For time 0, we asked people like what would be how the data would look like in probability terms, as I explained, and then 2.5 years, we got that data as well, and in these bars, this represents the probability. At age of 10, we asked it again, like the probabilities, and 17 years old, also how the probabilities would look like. So then we used that likelihood function, we estimate lambda, and then we plot the curve, and this is what the curve looks like. The dashed is the reference one, like how the true model will look like. And then in the experiment, then here the structure or the elicitation on the parameters. So 3 of those parameters were easy to say, but that S0 and S2 was hard to specify, such that the people participating in the experiment, they just put some random values. So this is, and then we calculated this alpha, as I said, like that represents or measures how well the model can reproduce the data from the experts. And this was bigger the predictive prior elicitation gave us a bigger alpha than the parametric or structural elicitation. So this is just remarks that we can work out of hierarchical models. There are also some computational challenges on it. We can work when this the prior prediction probability is given in closed form or not. We can using the priors. There are some, you can use covariates as well. This is just technical thing. One thing that at least nowadays comes to my mind is like, does the partition, the way that we partition the observed data influences or not, like the results? So maybe some direction would just use this linear measure of information to see if how we partition the observable space gives us better results. And